more from you, Kris. We are thrilled to have Kris Kitani with us. He's an associate research professor in the Robotics Institute School of Computer Science, and with courtesy appointments in Electrical and Computer Engineering ECE department, and director of the Master of Science in Computer Vision program at Carnegie Mellon University. He's also a research fellow in the Institute of Industrial Science at the University of Tokyo. Uh, we all know Kris. His research interests are computer vision, machine learning, autonomous systems. Uh, let's welcome him and have the talk started. Kris,
Yeah,
stage is
great.
yours.
All right, so thanks for the introduction. So I'll get started right away. I'm going to change the title a little bit. One of my PhD students was gonna be here, but many things going on this time of year. So I'll be talking about motion estimation and prediction using simulated physics. All right, so let's start with a pretty high level question. So this is for all you computer vision researchers out there that have thought about this for a while. What do you think it means to truly understand human motion? So when we observe human motion, we develop computer vision algorithms. Is it enough that we estimate all of the joint positions? Or do we need to go beyond that? Is it enough to know the exact mesh of a person while they're performing some motion? Or should we go even further than that? I don't think anybody's worked on this, at least in computer vision, is should we estimate skeletal muscular models from visual observations? So I don't know. I think we kind of are going to figure it out as a community, but what is the right representation? What does it mean to understand? But for the sake of argument, let's say, okay, maybe some mesh model is like you say, okay, that's sufficient for understanding human motion. And then the question is, okay, well, once you got the representation, what should the motion model be? Or what? How should we model that human motion? All right. So on one end of the spectrum, we have these kinematic models. They usually don't have any kind of physics constraints. It's more of just trying to estimate the skeleton and then how does that skeleton move. And moving and learning these kinds of models of motion are usually easier because there are less constraints, right? We don't have to think about the physics. I mean, it's still challenging, but relatively easier to learn. Now, the next thing we could do is we could say, well, we want to introduce some physics into the kinematic model, right? We don't want the estimates to be, arms bending backwards beyond like normal limits or feet sliding on the ground. So you might add some physics constraints to your kinematic model. So that's good. So that's probably where we are right now in computer vision. We could take this one step further, and we could say whatever motion model we learn should work in some kind of physics simulator. So it's having loose physics constraints is not enough. It needs to be hard physics constraints where you cannot violate the laws of physics. So that might be first step there might be simulated physics. And then the last one, if you were to take it another step further, it would be okay, if you had a computer vision algorithm, you observe a person doing something, you're going to be able to say that you understood that action if you could actually re-implement that in the real world using, you would need some kind of humanoid robot. All right, so I think this is the spectrum across which we can be thinking about what does it mean to understand human motion. And obviously on the right hand side, this is the hardest. It's most constrained. It's most challenging, hardest to learn. So, as computer vision scientists, how should we model human motion? So they're going to be different perspectives. So, it's going to depend. It depends. Some people might say, well, what do you want to use it for? If you want to just use it for surveillance, then maybe the physics doesn't really matter. It's more of, where are the people? But let's kind of step out of the kind of applications of it and think of it from a scientific perspective. Computer vision, we're trying to really understand what human motion is. What is human motion? So if you think about it like that, maybe, or where do we need to be on the spectrum as computer vision scientists or people who really want to know what human motion is? So like I said earlier, we're probably on the spectrum somewhere around here in CV. I think there's been a lot of work in kinematic modeling, right? So, well, first it started with 2D pose detectors and then temporal constraints, and we have many methods that try to match human motion to observations. And then we've seen work, from Adobe and robotics groups, where and computer vision groups where they're introducing physics constraints. But really, what's the ultimate test of perceiving human motion? Is this where we should be working forever? And kind of, I want to, I guess, put this idea in your mind is that maybe the ultimate test of human motion understanding is something like a physically embodied Turing test. So what does this mean? It means that if you were to look at a video of a person doing something and you learned a model of that human motion, we would know that you learned the true and real model if you could take that model and you could apply it to a humanoid robot and you could do the same thing. Okay, so it's kind of a maybe outrageous claim or outrageous goal. But who knows, right? Maybe 10, 20 years from now, maybe people in computer vision are all going to be roboticists. And that's how we're going to be testing our algorithms. It's not just bounding box detection or key point detection of body pose. It's going to be, okay, does your model actually work in the real world? Who knows? Okay, but maybe we'll be there someday. All right. So, I'm thinking, okay, one day we need to move to that right-hand side of the spectrum. How can we take one step closer to that? So I'm going to be talking about our first attempt of doing human motion estimation in a physics simulator, right? Or validating human motion estimates in a physics simulator with hard constraints, so not relaxed constraints. So this was our first try at it. It's an older paper, ICCV 2019, ego pose estimation and forecasting as real-time PD control. Okay, so just to kind of set this up, if I were to give you this egocentric video, so this is a person has a camera on their head and they're walking, can you guess the pose of the camera wearer? So you'll notice you can't see the body of the person wearing the camera at all. But the optical flow that you get from this video is a pretty strong indicator of body pose. So what do we want to do? What we want to do is we want to take this egocentric input video. We want to see if we can estimate the 3D pose of the camera wearer. So we have our estimate there in that the simulator visualization, and we actually have the just for reference, the third person ground truth there. So somebody standing on the side taking a video. So we want to estimate the pose, and we also want to forecast. So if we were to stop the egocentric video, could we continue to forecast what the person would be doing? All right, so this is kind of a dual task. So the method that we're going to develop is going to rest on this modeling assumption. So we're going to assume that human activity is a Markov decision process. So a Markov decision process, you might be familiar with it, is used a lot now. Reinforcement learning, but it's traditionally used for, well, okay, I guess traditionally it was developed more like an econ, but maybe you'll see it used more frequently in like a robotics context when you have some kind of embodied agent. Okay, so anyways, how does this modeling work? So the first thing we're going to assume is that if you were to take a human action sequence, we're going to assume that you can model that as a transition between states. So you could imagine the state being some, let's see, like the joint positions of the person. right? Maybe like, I don't know, 20 joints. Okay, that's the first part. We are also going to assume that the um, the the agent, right, who is trying to move from state to state, takes some action, right, according to something called a policy. So what is the policy? You could think of this as a probability distribution. I'm calling it pi over the actions it could take given the state that it's in. So if we apply this to a person, if I want to move to my next state, I'm going to, put strength into my muscles, and I'm going to propel myself forward. So that would be an action, and then the result of that action takes me to another pose. Right? Okay. So there's a name for this. The next state that you will be in, which is this st plus 1. Are you able to see my arrow? Yeah, the st plus 1. This is going to depend on what state you're in, st, and what action you take. And so given those two, it's going to take you to the next state. And there's going to be some probability distribution defined over that next state. So this is called the state transition dynamic. So you could think of this in the case of human activity as like the physiology of the human body, right? So depending on what kind of muscles you have and what your joint structure is like, that's going to determine the next state that you can take. And then there's also the physics of the environment. So there's the contact forces and the geometry of the scene. Okay. So what we're going to do is we're going to take this idea that human activity can be modeled as a Markov decision process, and we're going to apply it to our egocentric video-based pose estimation. So this is what it looks like now. We still have the same state sequence, although the state now is going to change a little bit. So the state, for the first example, I said it was just the joint positions. It's going to be joint positions, joint velocities, and a visual context. So you could think of the visual context. Well, actually, what we use it's going to be the optical flow that we get from the video. All right, so that's the state. The person will take some action. So I like actuating their body, putting strength into their limbs, and it's going to take them to the next state. All right. So we're taking that model. I'm going to draw the exact same idea now as an interaction diagram. So I'm going to abstract this a little bit. This is going to be important because I'm going to use this again later in another paper. All right. So let me show it to you one piece at a time. This is the MDP interaction diagram. Remember that the state, I've defined that as the joint angles. So there could be, if there are 20 joints, there's like a 20-dimensional vector there for joint angles, and then we'll have joint velocities. So again, that could be 20-dimensional. And then we have some visual context. So you could think of this as some optical flow field, and you could vectorize it, I guess. Okay, so that's the state. We're going to take that state and then pass it to the policy pi. And what does the policy pi represent? This represents the person. Okay, what the person. It takes in its current state, and then the person is going to act on that state. So it's going to take some action AT, and in the case of people, it's going to be how much torque do we apply to our joints. Right, and then same thing for the humanoid. How much torque is the humanoid going to apply to its joints? Okay, then we're going to take that action that was decided on by the human or the humanoid, take the current state, and then this is going to be passed to the environment, right? Or this is used to interact with the environment. So the environment is the physical, literally the physical environment, right? With all the physics and everything that it entails. Inside of this environment, we also have the egocentric video. This is a little bit harder to kind of explain conceptually, but it's saying, okay, if you take some action and you're in some state, this is going to create the next image or the next optical flow field. So out comes from the environment the next state, right? Because you took some action in some state. That's going to be your pose, your velocity, some egocentric features, visual features, and then you also get some reward, RT. Okay. So this is just an interaction diagram representation of what I showed in the earlier slide. Okay, so the reward part I didn't really explain. What is this? This is just it's another aspect of an MDP. This needs to be defined in like the most basic inference problem in an MDP, which is called optimal control or simply just solving the MDP. Okay, but anyways, we have to define the reward. So what is the reward for this MDP? So the idea of defining the reward like this comes from another paper. It's called Deep Mimic from CGraph 2018. Okay, the reward is it's a linear combination of matching against what your internal simulated humanoid is doing and what the ground truth 3D poses of the person. Okay, so this is so you should know that this is assuming during this reinforcement, during this training stage, we have available to us 3D motion capture information, right? And we're trying to match against it. So there's 4 different terms. First one's checking if the joint angles between your estimated humanoid and the motion capture humanoid, if they're similar. Second term is looking at the end effector, like hands and feet locations. Third term is looking at the root. So this is the absolute motion of the humanoid. Does it match the ground truth motion capture? And then also root velocity. Okay, so once you've defined the MDP, there are many algorithms for solving the MDP. Solving the MDP means solving for the optimal policy pi. I'm not going to go into reinforcement learning, the details of reinforcement learning, but the high level objective of reinforcement learning or optimal control or solving the MDP is to maximize your expected total reward of your policy. So you could write here as the expectation over probability distribution over trajectories. So it's like a sequence of states and actions, or in this case, a sequence of states. And you want to know the expectation of your total reward. Okay. All right. And so in this paper, we use something called PPO. And then once the policy is learned using PPO, we can use it to estimate human motion. So in other words, you give a state, you give it an image, and it will estimate what the pose is, basically, for each time step. All right, so let me show you a video of the result. All right, so top left, what we have is the just a reference third person point of view. We do not use this as input. And then on the right-hand side, we have our output of our algorithm, right? And you can see that it's doing a pretty good job estimating what the person is doing, even though you can't even see the person in the egocentric video. All right, so I think I'm already running out of time. But so let's keep going. Yeah, just to some different results. Okay, so that paper was our first step into doing full physics simulation with hard physics constraints. You'll notice that the results that we showed were of people like walking and running and bending down and bowing. So it's pretty simple. If we try to use our approach and directly apply it to more complex actions, you'll get something like this. So remember, we're using a version of Deep Mimic, so that's basically what we're doing. And then the right is the ground truth reference. And so if you try to mimic something like this dance move, what you'll see is it can't fully mimic it, right? So I mean, this is it's a really hard problem. It's learning a policy, even in simulation, is pretty difficult, especially for more complex motions like this. So we asked ourselves, okay, can we build models that mimic complex behavior better? Right. So this leads to our next paper, which we call residual force control for agile human behavior imitation and extended motion synthesis. Right. So the motivation of this paper was that when we consider the problem of trying to imitate or estimate, human motion, there might be some mismatch problems. So what will happen is that there's going to be a difference in the dynamics model, or what I was calling earlier the state transition dynamic. So what does this mean concretely? The model that we use in the physics simulator for the humanoid is not exactly the same body that we are observing in a video or in some motion capture sequence. So there's already a difference there. The physics simulator, we're using Mujoko, but at the end of the day, it's a model of physics, and so it's not exactly the same as the physics of the real world, right? It's like an approximation of it. So because of that and many other kind of mismatches between what we're observing or what we're trying to estimate, there are going to be just some activities that we're not going to be able to mimic, right? So how can we better address this dynamics mismatch? I mean, what do you think? I mean, we want to push towards having models that are physically valid, but at the same time, we know that our humanoid models will be limited, our physics will be limited. One thing that you can do just is you can face it head on and say, okay, we need better humanoid models. So I think that's a valid direction of research, and we know there are people working in that. We could say we need a better physics simulator, and that's certainly another valid direction of research, and people are working on that. Okay, or something else. So what we're gonna do is, or we're gonna cheat. Okay, we're kind of gonna go backwards, and you'll see what I mean by that. Okay, there's a lot to unpack here, but how much time do we have? No. Okay, I think it's okay to spend some time on this. So what we're gonna do at the high level is we're gonna introduce something like invisible forces that this humanoid can apply to itself. Okay. This is not physically possible. Like we can't do this in real life. Okay. But this is how we're going to model the humanoid. So what I have here up at the top, I have the traditional policy, right? Traditional policy takes the current state, gives some kind of action, and this is going to be some kind of torques applied to joints, and we have our state transition dynamic. What we're going to do is we're going to modify this policy by adding something called the residual force, and it's marked here as A tilde. Okay, and you can think of A tilde, like I said, as this invisible force that you can apply to your body. Right. So what's a good example? Like imagine you're losing your balance and you're about to fall back. You have this magical ability to like put force on your butt to keep you from falling down. Okay. So again, not realistic, but this is how we model it. And this is also going to therefore change the state transition dynamic, right? So now we have the actions that you can apply to the humanoid, and then these invisible residual forces. Okay. And then this leads to this new policy that you could think of it as having two actions, okay, or a higher dimensional action space. And this policy can be decomposed into the traditional policy, where it takes the current state and action that's applied to the humanoid, and then this residual force sub-policy, which is used to apply these invisible forces. Okay. The reward function that we use is the same as before. So this is the reward as time step t is going to be the imitation reward from like deep mimic or whatever else you want to use, and then we have this regularization reward. So what this reward is going to do is it's going to make sure we don't use too many invisible forces, because otherwise, the humanoid could fly, for example, and we don't want that to happen. So we have a regularization term that says, okay, you can't apply too many invisible forces, just a little bit, as much as you need to complete to mimic some activity. And what did I have? Okay, so I've already mentioned this earlier, but the introduction of this residual force is going to change the state transition dynamic. Okay, so more details are in the paper. We kind of have two versions of this, but I'll just show you the results. The high level result is that if you look at the reward, which is the x-axis, and you look at the number of epochs or iterations of reinforcement learning, you'll see that our RFC models will obtain more reward much faster than a model that doesn't have it. Okay. So I'm probably not going to get the third one, which I think is okay. Let me show you a sequence where using the residual force model, it allows us to mimic these ballet and kind of complicated dance moves much better than just a imitation learning approach without the residual forces. Which is kind of expected, right? The RFC model is advantage because it has these invisible forces that it can call on to help it balance, whereas Deep Mimic does not. Okay, so I think, yeah. So like I said, we're thinking about the spectrum. We started with physics simulation in that ICCV paper. And then we said, okay, we actually can't perform a lot of complicated models. So we're going to relax the hard physics constraints. We're going to introduce these like invisible forces. And it's the same thing as relaxing the physics constraints. So how did the community react? All right. So on one hand, we got a lot of like media attention. People are like, oh, this is a cool paper. This is the ultimate, show of, I guess, your visibility is if you were tweeted by AK29501. Okay. That's on one side. And then on the other side, we have our friends in robotics. I don't know if you know Jan Peters, but, very prolific author in robotics and pioneer in that area. And you could see his comment to our Twitter post. He's saying, this is not imitation. This is just visualization. Only when it transfers to another physically equally difficult system, you have imitation. And he ends his tweet by saying, buy a robot. Okay, so clearly Jan Peters is annoyed. So, I kind of talked about this earlier. I mean, this is probably eventually where we need to go as people working in human behavior, motion modeling, right? Is that our systems are going to be tested if it can actually imitate, and then that imitation needs to happen on a equivalent physically difficult system. Okay, so I think time-wise I'm up. I do have like a third part. I'll post the slides, and I want to talk about a new NeurIPS paper we have where we take into account some object interactions. But I think I will stop here. We skip to the end. Oop. And then if you have any questions, I can take them. If not, it's totally fine.
Awesome. Thank you, Kris. Any questions from the audience here? While people may come up with their questions or type in the chat, one quick note I wanted to make. First, thank you for the great talk. You mentioned human activities are Markov decision processes, and then he also showed the follow-up work that in some more complicated cases like dancing, the model is not doing good in prediction or even in some cases proper reconstruction of the pose. My question was, is this still the very first sentence that you wrote in your slides correct? Does it hold to say still like human activities are Markov decision processes? Is it a simplifying assumption, or is it I mean, was it taken because you wanted to solve a problem in a inverse reinforcement learning framework, or is it a more general assumption?
Yeah. So I think the question is, how valid is the MDP modeling assumption for
Yeah.
human activity? And um, what one general comment is, um, all models are wrong, but sometimes they're useful. That's the story of maybe all of us in computer vision, right? So I don't think MDPs fully, model human activity, human behavior, right? Um, there are some, I'm sure, non-Markovian things that are happening. So, but that being said, I do think it's a big step forward from a regular Markov state transition model, where we actually take into account like the decision process on top of like a forward model like an HMM or even like LSTM, right? So I think it's a step in the right direction. I don't think it's by any means like a perfect model for human activity and motion. But yeah, but it also gives us, from a practical point of view, it gives us like a bunch of algorithmic tools that we can also use to analyze sequences, and then decades of theory in that area. So I think that's also beneficial.
Exactly. Yeah. Yeah. Thank you. Thanks for the
Yep. Thank you very much.
insightful answer.
Yeah.
So I think that there is no other question from the
I have a question.
audience.
Actually,
That's okay. Go ahead.
I'm the person who asked lots of questions, and that means okay. Again, great talk. Thank you. Enjoyed, inspiring. Couple of I wish you could really have the third talk also could make it. Looks the title very, very attractive as well. Uh, 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 just a joke, but I was wondering if you could record it, give it to us. Let's share it later on. Back to the question. Simulated engine. This is the one step move forward. Simulated environment eventually has something as an underlying to model explicit physics. Means what we know exactly, but we can model the whole world. You know what I mean? And that's what we have also. Rita is not here as well. That means we can't. We don't know everything in the world. If we know it, it means all possible rules and models, and then eventually we are stuck somewhere with by explicit modeling. Human even understand physics without explicit modeling. Means people maybe understand gravity without knowing what the gravity is. And I'm trying to just say how far we can go to start really moving away from the explicit modeling and move to the implicit physics. Means implicitly, maybe, I don't know, learn it from multi-sensor modules and then use it in order to for example, for our models to generate something physically plausible. I don't know if I could deliver
I think I understand what you're saying is, like it's the implicit physics versus implicit physics modeling for different things. So for the physics model, the simulator itself, it has explicit, right, equations for physics. It's all written out in there. So in that case, there could be more research that says, okay, can you learn those physics like concepts from experience and then build a physics simulator? The humanoid that's actually working and kind of doing its learning inside of the physics simulator, it is implicit, right? The humanoid inside of it doesn't have some kind of model of the physics simulator. It interacts with it, it gets information from it, and then based on that, it's improving its policy. And the policy is just some multi-layer perceptron, so it doesn't have any like explicit physics equations inside of it. So I think it is doing the implicit, even though it's in this like simulated world. It is learning it kind of implicitly in that sense.
And then another question is in the model you have the Markov model, and then environment is kind of connected to this simulation 3D environment. Means how we can associate the real world with this environment. Means if person really moving up to the stairs, do you really
for like kind of working on that problem too. So I think that's a great question. And it's like an active area of research is
Sure.
how to get that transfer to work.
That's all.
Yep. Thanks everybody.